Okay, so uh, you all should be familiar with this model of bipartite graph, the Tanner graph that we have seen earlier, right? And so today we are going to think of this graph. We are looking at what is called a neighborhood of this graph. Actually, for this particular graph is the product code. Um, this is kind of a summary of how the connections in the H matrix looks like. But if you think about the entire set of connections, right? So uh, you can actually draw another layer where uh, this particular node would be then connected to this check node. So in the next layer, you will put squares, and then you will connect this node to this check node. And so it will create one more layer of the graph. And then beneath that, there'll be variable nodes, which also will be connected to the check nodes and so on. So actually, what we are looking at on this graph, or we later on went on to look at this type of very localized view, is actually part of a much larger picture that you would probably want to have in your mind. So I was looking at one such picture. Let's see. I was just looking at. Okay, so this is the picture that I was trying to convey to you. That now this is the same Tanner graph. It has square nodes and circle nodes, and this would be like one local neighborhood of the graph. But then the graph has been expanded out where this variable node is connected to. It is shown what all the check nodes this variable node is connected to. So it is connected to these three check nodes. And then these three check nodes in turn are connected to the corresponding variable nodes. And so it can go on like this. Okay, so actually the graph kind of expands. And the reason why it expands is because we are doing iterations. In the first iteration, the messages are being passed only between the nodes that are connected to each other on that Tanner graph. But then in the subsequent iterations, so going back to, let us say, right. So in the first iteration, the messages are being conveyed from the check nodes to the variable node, and then variable node will convey corresponding messages to the check node. But then subsequently, what this variable node has sent to this check node will send it to the other variable nodes that are connected to it, right? So that way, the graph at multiple iterations will kind of expand. So maybe one more picture I can show to you. So let's see. Okay. Just not able to get that this picture. It is nicely drawn in this textbook by sorry, just bear with me a little bit more. So this would be the visualization that I was trying to mention, that this shows how the messages are getting exchanged over multiple iterations of the graph, how the graph expands. Right? So this is a check node. It is connected to 4 variable nodes. Those variable nodes are in turn connected to the check nodes, the corresponding check nodes. And those check nodes are in turn connected to the variable nodes. And then those variable nodes will be passing the messages to their connection. So you can, the way to look at this graph is this circle stretches out and to the number of iterations that your algorithm is performing. And this view is kind of focusing on a particular neighborhood, and then it is looking out from there. And it's like a view with perspective. So as you go further away, the sizes are becoming smaller of each of the nodes, but it shouldn't take away the main message of this picture, that the message passing is to be really thought over, happening in this type of iteratively expanding graphical structure. Okay, so that is what I wanted to mention at the beginning. So now let us start from where we had left off. So for today, we are going to, oh, by the way, someone pointed out that there is a typo here. This 0 should have been 1. Okay, so in case you have noticed it, that is good. If not, keep that in mind. There was a mistake here on this slide. Okay. So over here also it should be 1. So we looked at the LDPC code. Now, what I wanted to highlight to you today is something which is very interesting. I mean, again, if you take it in with an inquisitive mindset, okay? You see that as a part of this project, you will be implementing this software, which is going to do message passing iterations, belief propagation. And then that software is going to generate certain results. Now, how do you know whether those results are correct or wrong? Could be that there is some bug in your software. Now, one way to do that is to say that if my program produces the same result, um, Jatin, you want to probably mute your microphone. Okay, so one way to kind of get confidence that your program is working correctly is to compare your result with what the others are opting. And if all of you are getting the same result, then yes, the chances are that all of your programs are correct. But still, there is a possibility that all of you might have made the same mistake, right? So uh, this is kind of a hypothetical situation that I'm saying, but uh, as the programs become more and more complicated, uh, you can never be sure about their validity uh, until and unless you come up with a completely different way of understanding the performance of the algorithm that has nothing to do with the program that you have written. It's entirely pencil and paper based derivation. Okay? Now you may think that this iterative algorithm, especially this progressively expanding graph that we were just looking at, I mean, what type of analysis can be done on that? Because it seems like a very complicated structure to analyze. But it turns out that at least for the binary eraser channel, uh, the performance can be derived surprisingly relatively easily. Okay. And that is what we are going to look at today. That is why I thought of spending one more lecture, because it gives an idea of the power of analysis, power of just pure thinking, mathematical thinking. And with that, you are able to get certain answer, which you know has to be true because it has been derived logically. And then now if your performance coming out of your simulator uh, agrees with what the analysis has told you already, then you know that your software, your program, your algorithm has been correctly implemented. And this we kind of have done in the context of BPSK demodulation earlier, where we analytically derived the error probability, and then through the simulation, we try to match it. Or we similarly did the same thing for repetition pool. So now we are going to do something which appears on the face of it far more complicated. The performance of LDPC. So let us see. Now, one assumption in this analysis is that we are assuming that uh, the LDPC code has an ideal bipartite graph, meaning that the graph has no cycles. Okay, so what do I mean by cycles? And so for that, I'm going to again try sharing more picture. Okay, so are you able to see the screen, by the way?
Yes, sir.
Yes, sir.
Yes.
Okay, so here I'm showing you a bipartite graph, and this graph has a cycle of length 6. So what is the cycle? I mean, you can kind of guess that if something kind of forms a loop, then you can call it a cycle. And so here we say that the cycle has a length of 6 is because if I start from this check node, for example, and this is where you have to start thinking of this graphical structure in terms of that progressively expanding structure that we were just now looking at. Because if it was just one iteration, the cycles won't matter. The problem is that when you do 3 iterations, then you will be hit with a cycle. And so what is the cycle? So let us say that we start out with this check node. And the check node has sent some message to the variable node. So this is 1. Then variable node will send a message to this check node in the same iteration. Or maybe in the next iteration, but or maybe let us do it more systematically. So remember, our iteration starts from variable node sending a message to the check node. So then instead of this check node, maybe let's start from this variable node where my cursor is. So the variable node has sent in the first iteration a message to the check node. And in the same iteration, the check node will send some message to this variable node because they are connected. So that is the end of one iteration, and the length is 2 so far. The number of edges that we have traversed is 2. Then in second iteration, this variable node will send a message to this check node. And then this check node will send a message back to this variable node. So we have traversed 4 edges. But cycle is still not formed. But then in the third iteration, see what happens. This variable node will send a message to this check node, and this check node in turn will send a message to this variable node back. And so we are back to where we started out, right? And the number of edges that it took us to come back to where we started out, sort of to complete a cycle on this graph, is 6. 1, 2, 3, 4, 5, and 6. So this is called a length 6 cycle. And this will become apparent if I draw another layer beneath this graph, describing what happens in the second iteration, and then one more layer beneath this graph. So there are 3 layers describing what happens in the third iteration. And then what we will see is that the message that originated from this variable node is kind of got looped back and it came back to itself. So remember, in our algorithm development, we said that we want to avoid loopback as much as possible, right? And so we made sure that at least within a particular iteration, we are not involving any loopbacks. Hello?
Yes, sir.
Okay, I was on mute. Actually, I got disconnected first, and then when I got reconnected, I had assumed that I will be not on mute, but I was on mute and my video was not on, so there was all sorts of technical problems. Um, anyways, so what I was saying is that in today's subsequent part of today's lecture, uh, we are going to do this analysis of the performance of LDPC codes. And the assumption behind this analysis is that we are having an ideal bipartite graph, a graph which doesn't have any cycles whatsoever. In reality, when you work with an H matrix, it will not be ideal graph. So the corresponding bipartite graph of that H matrix will not be ideal. It will have certain cycles, hopefully not of very small lengths, because as the cycle length becomes smaller, then that positive feedback becomes more and more amplified. So the designer of LDPC codes try to make sure that the corresponding graph of the LDPC H matrix has cycles of pretty large length. Okay, so we are going to assume an ideal version of it where the graph has no cycles whatsoever. By the way, the concept of a cycle and how to measure the length of the cycle is clear to you based on that picture we were looking at?
Yes, sir.
Okay, so when we go over this derivation, you're going to keep that type of iteratively expanding graphical structure in mind, okay, that perspective view that we have. Okay, so let us first look at what is happening on the check to variable nodes. Okay, so let us say that we are having a regular LDPC codes for which all the check nodes have same degree of DC. And these are some notations that, so this is a degree DC check node. So I'm going to draw a square here. And I'm going to see, I want to know the erasure probability on an outgoing message coming out of this check node when its remaining DC minus 1 these are the messages that are coming in from connected variable nodes. Okay, so this is, let's say, 1, and then this is DC. Right, so these are the DC variable nodes. And let us assume that the probability of erasers coming up from the variable nodes to this check node, the probability of erasure on the Tth iteration is P of T. And so T is the iteration count. So when T is equal to 0, that is the start of the iteration. And for that, the probability is P, the eraser probability of the channel itself. So now I want to ask you this question, and let us see who answers this. We are looking at what is the eraser probability on this message that is being sent, right? So this message. And remember, this message for the binary eraser channel, when will it be erased and when will it not be erased? Remember, this is a check node. the check node is a single parity check code. So the question is, when this DC -1 incoming messages to this check nodes have an eraser probability of E of t at the tth iteration, what is the probability of erasure of a message coming out of this check node? And so to help you answer that question, this is the observation, that for the outgoing message to be unerased, all of those DC -1 messages that are incoming from the other variable nodes, they all must be unerased, correct? Or more specifically, they must be unerased.
Sir, it will be 1 minus bracket of 1 minus e to power t to the power DC -1.
Okay, so Trupal said that it will be 1 minus e to the power t raised to the power DC -1.
Yes.
Right. So now this is the probability that the outgoing message will not be erased. Why this is the probability? Because ET is the probability that incoming message is erased. So 1 minus ET is the probability that the incoming message is not erased. And for this check node to produce an unerased output, all of these DC -1 messages have to be unerased. And so the net probability is this. Now, when the probability of a check node sending an unerased output is given as this, and I hope you have understood why this is the case. What is the probability that this check node will actually send an eraser? This is the probability that the check node
1
will,
minus of this.
yeah, so Kandar stated correctly, it will be 1 minus of this. So that is the first piece of the puzzle, that the probability that the check node will send an eraser, which I have labeled as E of TC, eraser coming out of a check node, is equal to 1 minus, and then in the bracket 1 minus ET raised to the power DC -1. Right? So this is how we can think of what will happen coming out of a check node. But we have to complete the full cycle before we can identify the performance of the LDPC code. So the remaining part of the cycle is variable to the check node. And we are going to again assume that all the variable nodes have the same degree. So again, the same graphical structure applies, that the outgoing message from a particular variable node over a particular edge towards a particular CN check node is a function of the incoming messages coming from the other DV -1 CNs. This is what we looked at last time. Now remember, this is the variable node is the repetition code. And so for this outgoing message to be an eraser, sorry, not Lth iteration, they should be Tth iteration. Or rather, let's call it T plus 1th iteration, because now we are ending the Tth iteration. So for the outgoing message to be an eraser at the next iteration from this variable node, what has to happen? First of all, the incoming message from the BEC itself has to be erased. And that has a probability of P that we are calling E0. And additionally, all of this DV-1 messages also have to be erased. That is the BEC algorithm at the variable node that we have seen last time. When all of the messages coming in at a variable node are erased, then only the variable node will send an eraser. Otherwise, it will always send a correct value. So what is the probability of this happening?
E of t plus 1 हो जाएगा.
Right. So the expression has to be for E of t plus 1. Correct. But E of t plus 1, how can I write it mathematically? Given that this is the case. Remember, the probability that any one of this DV-1 message is erased at tth iteration, we have already derived on the previous slide. It's already derived here. So all you have to do is
Is it
write an
e raised
expression.
to dv minus 1?
Yeah, exactly. But in addition,
Into P.
you have to consider this part also.
So p into e to the power dv minus 1.
Correct. So it will be E0 times E error at tth iteration for the seat for check node C, and this I have to raise to dv-1. That is the probability that the message coming out of the variable node will be erased. Right? So this is what I have written here. Now we have completed the entire cycle, and so we can also complete our answer. All we have to do is take the expression of ETC that we have derived earlier in equation 2 and plug it in here. And so then we get this final expression. So this expression is actually, you will see it's a function of only 3 variables. One is E0, which is equal to P, that is given to you, DC and DV. And then all that you do is make T equal to 0 and then increment T. And so when T is equal to 0, all that it is just E0. And then subsequently ET plus 1 will become a function of ET and E0, but ET was derived in the previous calculation. So this is the analytical derivation of how the eraser probabilities are changing with iteration index. And so we can plot it. We can use specific values of DC and DV and E0, and we can plot what happens. And so that is what I have done over here. So this one, x-axis is the T value, iteration index. It starts from 0 and then it goes up to 30 in this case. And then what are these different charts? They are for different values of P, the binary eraser channel probability. So this actually I should call E0 instead of E. And more, maybe I should have just called it P of binary eraser. So all of these E values are actually nothing but P values. There's a notation inconsistency. So we start with the binary eraser channel whose eraser probability is 30%. So it erases 30% of the bits. Then for that eraser channel, what this shows is that this ideal LDPC code which has no cycles, and the variable node have degree of 3, check nodes have degree of 6. Its error probability will start from 30% because that is the error eraser probability of the BEC itself. And as the iteration progresses, the erasers will reduce. And after about 7th iteration, the eraser probability will become 0. If you consider the little worse channel with 0.35, around 10th iteration, the LDPC decoder will unerase all the erasers. And then as you start making BEC more and more difficult, meaning that you increase the eraser probability, the algorithm will take more and more number of iterations before it converges. So for eraser probability of 0.41, it takes about 21 iterations. But at 21st iteration, it will have unerased as many as 40% of the erasers. If you go up to 0.42 erasers, 42% of the bits are erased. So error probability is 0.42. The algorithm will still converge. Maybe it will take more than 30 iterations, but it will still unerase all of them. But then surprisingly, from 0.43 onwards, the algorithm will fail to converge for this particular LDPC code. And it will not be able to unerase the bits. Okay, so this is in the textbook and in the literature. This is called the density evolution method. The name is fancy, but all it is just this particular derivation that we have done. And the main assumption is that the messages are not getting fed back, which won't happen if the graph has a cycle of some small lengths. So if the Turner graph has cycles which are pretty large, then this analysis is going to be more and more accurate. And from this analysis, we can derive the threshold value of P star, for which the algorithm converges. Maybe it will take lot of iterations, but it will definitely converge. The errors will become 0. And so based on the chart that we saw for this LDPC code with dV equal to 3, DC equal to 6, this threshold P star is about 0.43. So in your project, the H matrix that I have given you, actually you will see, I think, I'm not 100% sure, but at least one of the H matrix has this structure. dV is equal to 3 and DC is equal to 6. And so for that H matrix, I mean, assume that it doesn't have any cycles of short lengths, then your algorithm should be able to unerase and recover all the erasers for BEC, for which P value is around 0.4. And then if you make it higher than 0.43, then it is definitely going to fail. If it is less than 0.43, then your algorithm should actually work. Because of this type of assumptions, maybe the algorithm may not be able to pop up all the way until this 0.4294. But it should be able to cope up until about 0.41 list or 0.4. Okay, so this is a very simple but quite elegant derivation of the convergence performance of an LDPC code. And this is pure analysis. This chart that I drew here, you can easily calculate this chart by just programming this equation on your own, where you won't have to do any message passing decoder implementation. And you will be able to show how the convergence is happening. Actually, as a part of your project, I have asked you to generate the convergence charts coming out of your algorithm, coming out of your program. It will be a very nice thing for you to do if you show that this is the analytical convergence, as I've shown by these lines, and then you would plot the practical convergence coming out of your simulator, maybe in dotted lines, and you would see that the simulated and the analytical convergence profiles are roughly matching. If you do something like that, that will be very impressive. Okay, so that is topic number 1. Now I'm going to take a quick break and okay. So now the second topic for today is going to be actually more or less the last topic of this channel coding subject, which is going to be on the 2 questions, if you recall, that we had considered in the context of example where the transmitter was sending 1000 bits per second. Remember those 2 questions that I'd asked, and a lot of you had given answers which on the face of it they seemed correct, but then they turned out to be incorrect. And actually the correct answers were based on the mathematical formulation of the information transfer. And at that time we had kind of left this question, that why is it that how many bits get through the channel, let's say binary symmetric channel, what does it have to do with the information transfer formulation that we had done in the earlier part of the semester? And so we will look at not a complete mathematical proof, but kind of an argument for that. And this is what was the reasoning behind development of the channel coding schemes. So even the initial channel coding schemes such as repetition coding or single parity check code, but more pertinently the schemes that are used today, the LDPC codes or the polar codes or the turbo codes, they have to be thought in terms of this reasoning that we are going to lay out. And that way we can kind of connect the performance of the LDPC code with what the ideal performance should be. Okay. Now, when this binary symmetric channel is introducing some bit flips that happen with probability of P, if you want the receiver to get certain number of bits every second without any error, then what the transmitter has to do is to allocate some fraction of it, some fraction of this 1000 bits per second, so that using those fraction, the receiver can kind of recover from the bit flips. And the way to think about this is to think of BSC itself as a source of a binary string of length 1000 bits every second. And this is what actually you'll be doing in your project. You'll be generating binary symmetric channel and binary eraser models, which will be essentially zeros and ones. And whenever there are zeros, you don't touch those bits. Whenever there is a one, for binary symmetric channel, you flip the corresponding encoded bit of the transmitted code word. And for binary eraser channel, you erase that particular bit. So to see it mathematically, we'll say that received sequence is Y, which is XOR of X and N. X and N are both having 1000 bits every second. And N is this sequence with where the channel is introducing errors. So wherever there is a 1, For binary symmetric channel, the corresponding bit of X gets flipped. Right? So the first two bits came out correct. The third bit got flipped. The fifth bit also got flipped. And then eighth bit also got flipped because the, no, sorry. Now only third and fifth bit got flipped because this AND has ones in only third and fifth location. This is showing only for 8 bits, but in reality, all of these sequences will have as many bits as you are transmitting. Right. So this is the way we want to think of binary symmetric channel or binary eraser channel in terms of this sequence N. But now let us go back to the concept of typical SAT that we had studied towards the end of data compression topic. And we want to start thinking of this binary symmetric channel, which is generating this random sequence of zeros and ones. We want to think of it as a binary DMS, which is generating some length capital N bit string in which the probability of 1 equals P. The question is, as capital N becomes longer and longer, sorry, N becomes larger, and so the sequence becomes longer and longer, how many different binary strings can be introduced by the BSC? That is the question. Who can answer this?
Two raised to n.
Accused shade 2 raised to n. But remember, this DMS has a probability of P for getting a 1. So it is really, yeah.
So this should equal the number of sequences of the noise.
Yeah. So what is the expression, mathematical expression for that? Think of the typical set. What is the size of the typical set? Remember, we went over this detailed derivation. 0.4 times 2 to the power n. What is the data compression limit?
NCNP.
If a discrete memoryless source is a binary source in which the probability of occurrence of 1 is equal to P, then what is the entropy of that source? Okay, so I see that some of you, maybe many of you, are a little bit fuzzy and vague about the concept of typical sets that we had studied at the end of data compression topic. So maybe you want to go back and revise that concept. But there, what we had concluded was that for small values of n, we can't specifically answer this question. Actually, for small values of n, all of the 2 to the power n sequences are possible. But as n becomes infinity, this BSC introduced noise pattern n gets trapped into a typical set whose size is 2 to the power n times the entropy. Okay, and therefore instead of n bits, we need n times HB of P bits. This is what we had studied in the data compression topic. So the way to think about it is that when you transmit a length n bit, sequence, it can turn into 2 to the power n times HB of P sequences. This is sort of like that Hamming sphere that we were drawing. Except now we are saying this with certainty that if I transmit this code word at the center, there is no way that it can become any one of the received sequence other than the ones which are shown in the black. Because if it were that were to happen, then this typical set is not occurring. But typical set always occurs with probability of 1 as n tends to infinity. And so we are kind of guaranteed to see that this green circle, which is the transmitted code word of length, of certain length, it is guaranteed to become any one of this black circle, and the size of this oval is 2 to the power n times HB of P. So the idea is that we transmit the code words, we design our channel code such that when we transmit this code word, the receiver sees this particular oval, and this oval or the sphere is non-overlapping with the corresponding oval for some other code, and so on. So we keep all of this 2 to the power n times HB of P subsets to be non-overlapping. Because when that happens, the receiver will see any one of these black circles, and by minimum distance decoding, it will always go to the center, meaning it will always be able to correctly decode. The error probability will become 0. And this is happening because of the same reason as what we had seen in context of the typical set and the context of why the entropy gives the lower bound on data compression. And so if you're transmitting n bits over binary symmetric channel, we need n times HB of P bits to isolate the error introduced by the binary symmetric channel. Why n times HB of P? Because that is the answer that we got over here. So to isolate where the error has happened, we need n times HB of P bits. And therefore, we can send the information over the remaining n times 1 minus HB of P bits. So the answer to those two questions, question 1 and question 2, was that if we are sending 1000 bits per second over a binary symmetric channel, when n is 1000, and those bits are going over this binary symmetric channel with probability of P of bit flips, then we cannot send more than 1000 times 1 minus the entropy of the binary symmetric channel. Those are the bits on which we can put information. The remaining bits we have to dedicate to be able to separate out the effect of the noise introduced by the binary symmetric channel. So in the context of this diagram, the overall size of this set is 2 to the power n. the size of each of these ovals, small ovals, is 2 to the power n times HB of P. This is the typical set formulation of the binary symmetric channel considered as a DMS. And therefore, the number of green circles, the number of code words, which is the number of green circles, equals 2 to the power n divided by 2 to the power n times HB of P, which is 2 to the power n 1 minus HB of P. So this was the answer that came out through the information transfer function also. So let's not go over the slides. If you wish, you can read about this detailed explanation on your own. It actually says the same thing which I said just now. So yeah, basically if you look at a source encoder and then what happens after the source encoder, the diagram looks like this. The source generates some data of length n bits, but the typical set has the size of only 2 to the power n times the entropy. So we need smaller number of bits to represent the source output. But then we kind of blow up the compressed output of the source encoder and we make it larger length. But this time, the way we make it to be a larger length, we introduce this black dots in a proper manner. Here they are like arbitrarily. We have no control over this. The channel encoder kind of introduces these extra sequences in a controlled manner so that decoder can recover from the message errors. So n times n times n minus n times HB of P is the maximum bits that can be transmitted. And the graph looks like this. And this is the maximum rate of the information transfer. So the maximum possible rate of information transfer is 1 minus HB of P for binary symmetric channel. And this is nothing but the information transfer function that we had derived for the binary symmetric channel. When we answered that question number 2 earlier, the information transfer function was exactly this, 1 minus HB of P. So this is kind of giving you an outline of how this channel coding schemes, how well they can perform. The rate of the channel coding scheme cannot become greater than this. The earlier channel codes, LDPC, the repetition code and the single parity check codes, they were very weak. The Hamming code was an advanced version of code, but still it didn't achieve this channel capacity bound. Then came convolution codes. They started performing better, but still nowhere close to this C. Turbo codes were one of the first codes which started approaching the channel capacity. And then today, LDPC and polar codes are also very efficient in terms of achieving this channel capacity. And for the analog channels, by the same argument, Ix of y turns out to be having this formulation. The entropy of y for the analog channel is given by this formula where PS is the received power and PN is the noise power. And entropy of Y given particular transmitted code word is given by this value. And so the information transfer function is given as this, which simplifies to this. And then if you're transmitting this signal over bandwidth of W, then you have to multiply this expression by W, symbols per second. And so you get final answer, which is the celebrated channel capacity theorem, which you have studied in lab 1. So this equation, which is even today driving a lot of research and development in the academia as well as in the industry. We didn't get into where this equations came from, log base 2 of PS plus PN and log base 2 of PN. But overall, you have kind of an idea of where this equation originates from and what is the underlying conceptual derivation. It has to do with the concept of typical cells. Okay, so that is all. So we are done for today. And then now from next lecture onward, we will start working on the modulation.